Let's start solving this problem. Maximum sum of a pair with equal sum of digits. Uh, you are given a zero indexed array nums consisting of positive integers. You can choose two indices I and j such that I is not equal to j, and the sum of the digits of the number is equal to the sum of the other chosen index value. So, among these, return the maximum value of num of I plus num of j that you can obtain over all possible indices I and j that satisfies the condition. Okay, let's take an example. So, we have to choose a pair, let's say anywhere between, let's say 18 and 36. And the sum of the digits for an 18 is 9, and some of the digits for 36 is 9. So, which are both are equal. And so, if we sum 18 plus 36, we get 54. Likewise, uh, if we do the same for all possible pairs and pick pairs having the same digit sum, uh, we'll pick the maximum out of it. That will be our answer. So the constraints here are number of elements in the array is 10 power 5, and each value in the array lies between 1 to 10 power 9. So uh, my initial approach would be like if we generate all the pairs, it will take n square, and 10 power 10 will not be feasible. So we will have to think of a better solution. So how can we convert n square solution to a linear time of n? Uh, the catch is we have to only look for pairs having the same digit sum. So how we can get all the pairs having the same digit sum? Let's say if we know the digit sum, we can group them in under one bucket. And once we have group them by digit sum, then we can do some operations like so let's say there is a digit sum 18, let's say, and we'll group all of them, and we will pick the top two maximum elements will give the necessary answer. Similarly, for all the group, we'll take the global maximum out of it. So to do that, we will process each element in the array and we'll calculate the digit sum. Uh, for calculating the digit sum, it will be constant, and we will do for n elements. So that we'll group each of the element and we'll keep it in a some kind of data structure that will give us top to larger elements. How we can solve this sub problem? So if you want to get the top k elements, we can have some kind of heap that will have minimum top maintain in the top will give always a minimum, and if you maintain a size of k and whenever it exceeds the k we will poll the element such that the minimum will be out of the heap, and at the end we will be having the top k larger elements. So, and we for the grouping we'll need an hash map, some kind of mapping we have to make. So we will be using an hash map for the grouping part, and for larger top k elements will be using heap, which is like a mini heap. So now let's it. So we will be needing a map for sure, which is of integer. And by default, Java provides min heap. So we'll be iterating over now. Now, so let's get digit sum. What we will do is we'll calculate a digit sum. So let's implement digit sum. How will we calculate? While the number is not equals to 0, then modulo division 10, which will give the last digit. And we will add it to the digit sum and we will divide the number by 10. So the rightmost digit will be removed and we'll keep doing until the number is 0. By the end, we will be having the sum of the digits of the number. Now this part is completed. Now we'll try to keep group digit sum man dot compute is absent. Let's try to keep the digit sum, and if it is there, it will return whatever the value present at the key, else it will create. Here we need a min key, so penalty q, and it will return it. So we will be adding num to it. Now, what we'll have is min man dot get of min if min heap dot size. Here let's define a k instead of hard coding. So whenever this size is greater than key, we'll just remove the top element, which is minimum element from the key, from the key. So by the end of the process, we group numbers and we will be having the top two k elements are, are in the heap. Now for each priority queues, like for each minimum heaps, so man dot get values. So we'll declare a max something. Let's say there is no pair exist which is having digit sum equal. In that case, we'll have to return -1. There is a test case for it. So Let- So this will have the maximum pair, maximum sum pair. That's after processing here. So maximum sum pair is equals to max dot. So we need the maximum. So map we can only do this if main heap dot size not equal to k. We will just continue, else it will be having k size k. So main heap dot poll plus main heap dot poll. So we will take the first largest and second largest and sum, and we'll be taking the maximum out of it. So I think that's it. It will so let's define where and the so let's try to run this one. So there is a syntax error. I think this is map dot values. Yeah, now both the test case are passed. Now I'll try to submit it. It got accepted. So let's define time and space complexity. Time and space. So we are processing n elements, and let's say n is a number of elements, and here we are creating a priority queue of size 2, and we are calculating digit sum. So this will be a constant time because this number will be 10 power 5, 10 power 9, so which is an int range, so maximum will be having 32 digits. So it will be constant, and so n times constant. And here these operations are constant time. Here it is 12. And so this, since the k is 2, this pole will also be actually logarithmic time. So since k is very small, it will be also a constant time. So this overall for loop will take linear time, and here let's say if all the digit sums are unique, so it will take a linear time again. And this pole operation is also logarithmic time, but the k is small, so it will be constant time. So the overall complexity will be big of n, and space complexity will be like we will be using an hash map and a priority queue. And since the 10 power 9, the maximum sum we can get is 9 power 9 times 10, which is 90. So, mm, which can be a constant time, we can say, based on the input range. But let's say if we consider it as an infinity, it will be taking linear time as well. So you can see time and space complexities here. It still shows n log n, but k is very small. And that's it. Thank you for watching the video. We'll see you next time.